Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Evaluation of the condition of Ngancar Dam in Wonogiri Regency is reviewed from the safety aspect of the dam. Hendra Wahyudi Civil Infrastructure Engineering Department, Institute Technology Sepula November, Sukolilo, Surabaya, Indonesia. Abstract Ngancar Dam is one of the dams that managed by Balai Besar Wilayah Sungai, BBWS, Bengawan Solo. Ngancar Dam is built on Jarak River, precisely located in Selopuro Village in Baturetno Sub-district and geographically located at 70485 LSN 1105353 BT. In addition, Ngancar Dam is also a historical building because it was built during the Japanese colonial era in 1944. In 1976 the Republic Indonesia government built Gajah mungkur, then it made Ngancar Dam located upstream. After approximately 75 years of more operation and various maintenance during the operation and the enactment of various regulations set by the government, especially regulations issued by the Ministry of Public Works and Housing of Republic Indonesia No 27/PRT/M/2015 on dams that emphasize the safety aspects of the operation process, then it is necessary to conduct a review of the condition of Ngancar Dam if reviewed from the safety aspect of the dam after carrying out its function. During this time, by using hydrological analysis to calculate flood discharge and hydraulic analysis to calculate water depth and analyze cremation and stability analysis by using GeoStudio software 2012 and supported by non-instructional testing with hammer test method to know the strength of concrete quality. The results show the condition of Ngancar Dam is reviewed from the safety aspect of the dam is still in a safe state because in the event of maximum flood discharge, QPMF equals 256,487 m3/SEC, there is no overtopping, no deformation in static conditions or dynamic conditions, and cracking on the dam at the time of flood or normal water is still smaller than 0.1% of the discharge of the base flow that enters Ngancar Dam. Keywords: Ngancar Dam, Safety Aspects, Government Regulation, and Safety 1. Background: Ngancar Dam is one of the dams managed by Balai Besar Wilayah Sungai, BBWS, Bengawan Solo. Ngancar Dam is built on Jarak River, precisely located in Selopuro Village in Baturetno Sub-district and geographically located at 70485 LSN 1105353 BT. In addition, Ngancar Dam is also a historical building because it was built during the Japanese colonial era in 1944. In 1976 the Republic Indonesia government built Gajah mungkur Dam, then it made Ngancar Dam located upstream. Ngancar Dam has the function to irrigate rice fields in Teman irrigation area, which has an area of 637 hectares with intake building in the form of a sewer-shaped tapping tower with a diameter of 1.5 meters and has a length of 65.7 meters and is arranged with a regulatory door that has a width of 1 meter and a height of 1 meter. Ngancar Dam is a dam of ground and stone layer with zonal clay core with dam peak length of 179 meters and dam height of 20.5 m at elevation of plus 250.54 meters and peak width of 5 m. with a guard height of 0.9 m and has upstream slopes with a ratio of 1:3 and downstream slopes with a ratio of 1:1,5. This dam has a concrete building with a wide threshold with a width of 34.10 meters at an elevation of plus 248.70 meters above sea level with the ability to drain water by 201.73 m3/SEC and has a launcher channel of 84.75 meters and has a type of O-lock pond as a water energy silencer in the form of USBR Type 3 made of concrete. The dam is in flood condition at an elevation of plus 249.49 mdpl capable of accommodating flood water of 3.05 million m3 while in normal conditions with elevation plus 248.70 meters above sea able to hold water of 2.15 million m3 and at minimum conditions at elevation plus 236.18 mdpl able to hold water by 0.89 million m3. After approximately 75 years of more operation and various maintenance during the operation and the enactment of various regulations set by the government, especially regulations issued by the Ministry of Public Works and Housing of Republic Indonesia No 27/PRT/M/2015 on dams that emphasize the safety aspects of the operation process, then it is necessary to conduct a review of the condition of Ngancar Dam if reviewed from the safety aspect of the dam after carrying out its function. During this time, 2. Problem formulation based on the background described above. The research on evaluation of the condition of Ngancar Dam in Wonogiri Regency is reviewed from the safety aspect of the dam can be formulated the following problems, namely how the safety condition of Ngancar Dam if reviewed from the safety aspect to carry out its operations. 3. Problem limitations. Research conducted with evaluation of the condition of Ngancar Dam in Wonogiri Regency is reviewed from the safety aspect of the dam has the following limitations. Aspects of dam safety include hydrological and hydraulic aspects, structural aspects, and aspects of the dam, while the understanding of each aspect is to include IJERT 10 is 060119 www.ijert.org 340. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 1. Aspects of hydrology and hydraulics, namely dams are able/safe to drain flood water so that there is no overtopping. Two aspects of the stability of the dam body include the ability of the dam structure to withstand static loads as well as dynamic loads. 3. This aspect of the spill includes the ability of dams to withstand water from piping hazards. While the safety aspect in carrying out operations related to water availability in this study was not carried out, review. 4. Expected benefits and objectives. The benefits and objectives to be achieved from this research activity are: A. The benefits of this research, when viewed from the science side, are expected to add to the benefits of science, especially the issue of dam safety. B. The benefits of this research can be used as a guideline for policy makers in managing dams because dams, in addition to carrying benefits, also save potential disasters. 5. The foundation of theory. The design flood hydrograph in this study used Nakayasu synthetic unit hydrograph method. With the following equation form, equals 3,6, 0,3, plus 0,3, where QP equals peak flood discharge, M3/CSEC, RO equals rain unit, mm, TP equals time log from the beginning of the rain to the peak of the flood, hours, T 0.3 equals time required by decreased discharge, from peak debit to 30% of peak debit, hours. Filtration capacity is water flowing into hilly through the body and foundation of the dam based on the jarring of filtration flow routes that can be calculated by the following equations. Figure 1. Trajectory network on a Urigan dam equals times where QF equals rim basin capacity, M3/CSEC, NF equals the division number of the filtration flow route line, NP equals the number of divisions of the equipotential line, K equals filtration coefficient, M3.dt, H equals total water pressure height, M, L equals transverse profile length. A dam is declared safe against cracking that occurs when the critical rim basin speed, VC, the speed of the spill, VS. Rim basin analysis uses GeoStudio SEEP/W software based on finite element. The result of the calculation is flux, i.e. discharge, Q, of the spillway that passes through the dam with the treatment of the surface condition of the reservoir in a flood state, FWL, and the condition of the reservoir in normal water conditions, NWL. The stability of the dam slope is analyzed using the Bishop method, assuming the total normal force works in the center of the P space and can be determined by deciphering the force on the piece vertically, normal. Balance requirements on the pieces that make up the slope as seen in the following image. IJERT 10 is 060119 www.ijert.org 341. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. Figure 2. Styles that work on a slice description, W equals total weight on slices L, ER equals style between slices working horizontally on the left and right cross section XL, XR equals the style between slices that work vertically on the left and right cross section. P equals total normal style on slices. T equals slide style on the base of the slice. B equals width of slice. L equals length of slice equals slope angle. Taking into account the entire balance of styles, then the formula for the security factor, FK, of the Bishop method is obtained with the following equations: plus 10 equals sin with the level of security factor value presented in the table. Table 1 FK security value level in practice FK description 1,5 stable 1,07 FK 1,5 critical 1,07 unstable 6. Research method. The research method is the whole stage of research conducted from start to finish so that a conclusion can be drawn. The steps can be seen in Figure 3. The following. Figure 3. Research flow chart 7. Results and discussions. Hydrology analysis is a basic analysis that must be done to evaluate the safety of the dam because the overall analysis of the water building of the pumping system depends on this analysis. Hydrology analysis in this study used data from TRMM from 2000 to 2019 as calibration data, while stations around the site include Baturetno, Giriwayo, and Ngancar, and Batuwarno stations because the data at the surrounding stations is incomplete, especially from Batuwarno station. No data from 2004 to 2011 with a watershed area of 693.7 hectares. For more details of Thiazena watershed and polygon shape can be seen in Figure 4. IJERT 10 is 060119 www.ijert.org 342. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. Figure 4. Thiesson watershed and polygon shapes. By knowing the rain of the area with Thiesson polygon, It is determined rain plan while to determine the size of the flood plan by using Nakayasu method. The results of the flood discharge plan can be seen in Table 2. Table 2 Debit Flood Plan No Reset Debit, M3/S,
159495 and 1/2 PMF 132.7439 PMF 256.487. The flood discharge plan is checked by Krieger method with the results can be seen in Figure 5. 10,000 1000 C30 C80 C100 QPMF Nakayasu QPMF Gamma IQPMF ITB1 QPMF ITB2 Graphic Krieger 100 Debit Maximum, M3/DT, 1001 10100A, KM2, Figure 5. Krieger Method Graph IJERT 10 is 060119 www.ijert.org. This work is licensed under a Creative Commons Attribution 4.0 International License. 1343 published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021. To evaluate the safety of dams against the danger of overtopping, a flood search is carried out on reservoirs that pass through the reservoir with the form of flood tracing as in Figure 6. Figure 6, Hydrograph of Ngancar Dam Flood Search. While flood search results against high guard can be seen in the following Table 3. Table 3. Water level elevation at spillway with high guard Kala Olang Q outflow elevasi Muka Tingi Jagan Q inflow max HD max reduxi Punkake Banjir max air, parapet, Kitarangan, M3/det, 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 percent, M, Q 100 128.63 82.83 1.21 45.79 35.60% 249.915 1.19 Tidak overtopping Q 1000 TH 229.89 163.10 1.85 66.79 29.05% 250.550 Q 1/2 PMF 132.74 93.42 1.3 139.33 29.63% 250.0 100.55 Tidak overtopping 1.09 Tidak overtopping QPMF 265.49 201.73 2.11 63.76 24.02% 250.8080.29 Tidak overtopping Kondisi Muka Air Normal Elevasi Punkake Bendunan Elevasi Parapet Punkake Bendunan 248.70 2.40 250.50 251.10 From the hydraulic aspect done with a review of the ability of Palimpa to drain floods. The results can be seen in Table 4. Table 4 Water face in Palimpa when flooding Kala Olang Debit Banjir Elevasi Muka Air Tinggi Muka Kesapatan Air Pada Air Saluran Peng Araki Darangan, M superscript 3/DT, MDPL, M/DT. Kesapatan 4 M/DT, Q 179.535 249.884 1.184 1.98 Among Q 1000. 158.472 250.518 1.818 2.57 Among Q1/2 PMF 89.942 249.979 1.279 2.07 Among Q PMF 195.163 250.785 2.085 2.76 Amon Elevasi Punkake Dinding 251.180 2.480 Elevasi Crest Palimpa 248.700 Analysis of dam body stability using GeoStudy software with a review of normal water conditions, flood water conditions and rapid low tide conditions can be seen in Tables 5 through Table 11. IJERT 10 is 060119 www.ijert.org 344. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Table 5. Stability of Ngancar Dam Body against landslides under normal water conditions Table 6. Stability of Ngancar Dam Body against landslides in flood water conditions Table 7. Stability of Ngancar Dam Body against landslides Indiana rapid low tide conditions IJERT 10 is 060119 www.ijert.org 345. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Beban y/h equals 0.25 y/h equals 0.50 y/h equals 0.75 y/h equals 1.00 Table 8. Deformation checks due to simulation of avalanche in empty conditions. Liran Hulu 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 KY 0.564 0.579 0.579 FK 1.000 1.000 1.000 K max, MD 0.727 0.785 0.732 KY/K max 0.775 0.737 0.791 UM 8.5 0.10 0.65 0.45 Kidarangan UM 8.5 Tidactor Jadi Deformasi Tidactor Jadi Deformasi Tidactor Jadi Deformasi Hulu 0.550 1.000 0.678 0.811 0.20 Tidactor Jadi Deformasi FK Simulasi 0.803 0.773 0.801 0.832 Table 9. Deformation checks due to simulation of avalanche in normal water face conditions. Beban Liran KY/FK K max, MD, y/h equals 0.25 Hulu 0.666 1.000 0.727 KY/K max 0.916 8.5 Kidarangan FK Simulasi 0.90 Tidactor Jadi Deformasi 0.877 y/h equals 0.50 Hulu 0.695 1.000 0.785 0.885 0.60 Tidactor Jadi Deformasi 0.838 y/h equals 0.75 Hulu 0.669 1.000 0.732 0.914 0.40 Tidactor Jadi Deformasi 0.874 y/h equals 1.00 Hulu 0.640 1.000 0.678 0.944 0.19 Tidactor Jadi Deformasi 0.915 Table 10. Deformation checks due to simulation of avalanche in flood water face conditions. Beban Liran KY/FK K max, MD, y/h equals 0.25 Hulu 0.648 1.000 0.727 y/h equals 0.50 Hulu 0.669 1.000 0.785 y/h equals 0.75 Hulu 0.669 1.000 0.732 KY/K max 0.891 0.852 0.914 UM 8.5 Kidarangan FK Simulasi 1.83 Tidactor Jadi Deformasi 0.854 0.89 Tidactor Jadi Deformasi 0.808 0.80 Tidactor Jadi Deformasi 0.842 y/h equals 1.00 Hulu 0.620 1.000 0.678 0.915 0.80 Tidactor Jadi Deformasi 0.881 Table 11. Deformation checks due to simulation of avalanche in rapid receding conditions. Beban Liran KY/FK K max, MD, KY/K max UM 8.5 UM 7.5 Kidarangan UM 8.5 FK Simulasi y/h equals 0.25 Hulu 0.373 1.000 0.727 0.513 0.80 0.12 Tidactor Jadi Deformasi 0.673 y/h equals 0.50 Hulu 0.368 1.000 0.785 0.469 100.20 0.11 Jadi Deformasi 0.650 y/h equals 0.7 Hulu 0.368 1.000 0.732 0.503 0.79 0.11 Tidactor Jadi Deformasi 0.671 y/h equals 1.00 Hulu 0.373 1.000 0.678 0.551 0.67 0.10 Tidactor Jadi Deformasi 0.694 Test concrete strength. By conducting non-destructive test using hammer test tool at the location shown in Figure 7. IJERT 10 is 060119 www.ijert.org 346. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06. June 2021 Figure 7 Location checking concrete strength with hammer test tool. Non-instructive testing using the hammer method can be seen in Table 12. Table 12. Hammer test results. Code location test result, MPA, A. Dinding Merku Kiri 38.28 B. Dinding Merku Cannon 40.33 C. Merkusa C. Cannon 41.56 D. Merkusa C. Kiri 35.44 E. Lantai Palunker Addis 35.61 F. Lantai Palunker Bawa 37.50 G. Block Halen 37.67 H. Dinding Palunker Tengasa C. Kiri 34.67 I. Dinding Palunker Tengasa C. Cannon 38.78 J. Lantai Palunker Tenga 41.78 K. Dinding Palunker Bawasa C. Kiri 38.17 L. Dinding Palunker Bawasa C. Cannon 36.00 M. Lantai Palunker Bawa 45.56 N. Block Halen Bawa 38.60 Average.
38.57 Based on non-destructive test results with hammer test method shows concrete condition is still in good condition because the quality is greater than FC equals 20.35 MPa. The simulation of rimbeson on the body is reviewed in normal water phase conditions, flooding and rapid receding, which can be seen in figure 8 up to the following image. IJERT 10 is 060119 www.ijert.org 347. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Figure 8 Simulation of spills on the dam's body under normal waterfront conditions. A review of dam conditions resulting from the spillway during normal water review at point A shows the condition of the discharge of the water is 1008 x 10 to 7 m3/c/sec 1% Q base flow equals 0.0956 m3/c/sec while the safety factor against piping equals 3571.5, safe. Figure 9 Simulation of the impact on the dam's body in flood water phase conditions. A review of dam conditions caused by the spill during normal water review at point A shows the condition of the discharge of the water is 1089 x 10 to 7 m3/c/sec 1% Q base flow equals 0.0956 m3/c/sec while the safety factor against piping equals 3256.1.5, safe. IJERT 10 is 060119 www.ijert.org 348. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Figure 10. Simulation of fracturing on the body of a dam at rapid receding conditions. A review of dam conditions resulting from rapid low tide was reviewed at point A indicating a 4729 x 10 to 8 m3/sec 1% Q base flow equals 0.0956 m3/sector 8. Conclusion. The conclusion of Ngancar Dam condition if reviewed from the aspect of dam safety are 1. Dam safety from hydrological and hydraulic aspects shows results in the event of PMF flooding of 265.49 m3/sec. Then Palimpa is able to drain flood discharge by 195,163 so that it does not overtopping occurred. Dam safety reviewed from the structural aspect shows a strong concrete flat press yield of 38.57 MPa of the permitted minimum strength, FC equals 20.35 MPa, and at the time of static and dynamic conditions there is no deformation of the dam body. 2. Dam safety is reviewed from the rimbeson aspect showing the result of the spill result at the time of flood water level of 1089 x 10 to 7 m3/sec 0.0956 m3/ section concluded that the condition of Ngancar Dam is still in a safe state if it is reviewed from the safety aspect of the dam. Reference 1 Anonymous, 2015, Perman PUPR Nomer 27 Tahun 2015 Tentang Bendunan. 2 Anonymous, 1998, Dam Structures Surveys Pakit Sid C5, Laporan Rehabilitasi, Tidak Dipublikasikan 3 Dak, 2002. Hydrology Dan Penjlolandara Aliran Sugai. Gajah Mada University Press. Yogyakarta. 4 Bishop, A.W., 1955. The Use of Slip Surface in the Stability of Analysis Slope, Geotechnique, Vol 5 London 5 Bowles, J.E., 1984. Physical and Geotechnical Properties of Soils, McGraw-Hill Book Company, USA 6 DOS, Braja M. 1985 Principle of Geotechnical Engineering, 3rd ed., Southern Illinois University, PWS Publishing Company, Boston 7 Chow 1964, Handbook of Applied Hydrology, New York, M.C. Graw-Hill Book Company. 8 Chow, V.T., David, R.M., Larry, W.M. 1998. Applied Hydrology. New York 9 Cordery, I 1991. Estimation of Design Hydrograph for Small Rural Catchments. Journal of Hydrology No. 13. Tenfan, J. and Morris, G.L. 1995. Reservoir Sedimentation Handbook, Design and Management of Dams, Reservoir and Watersheds for Sustainable Use. New York, McGraw-Hill. 11 Frevert, R.K. 1959. Soil and Water Conservation Engineering. New York, John Wiley & Sons, Inc. 12 Gordon, N.D., T.A. McMahon and B.L. Phenolison. 1992 Stream Hydrology and Introduction for Ecologist. John Wiley & Sons Ltd. New York. 13 Gray, D.M. 1961. Synthetic Unit Hydrographs for Small Watersheds. Journal of Hydroelectric Divasce. July. High 4. 14 Gray, D.M. 1970, Handbook on Principles of Hydrology. The Iowa State University Press, Ames, Iowa. 15 Gregory, K.J. and D.E. Walling. 1977 Drainage Basin Storm and Process. Edward Arnold Publishing. Limited, London. 16 Gupta, S.N., A.P. Bhattacharya, S. Arjindal. 1967 Statistical Correlation of Himalayan and Bundelkhand Basin Characteristics with Flood Flows, Floods, and Their Computations, Proceeding of Leningrad Symposium, IASH, UNESCO, WMO, Geneva. 17 Hahn, C.T., H.P. Johnson, and D.L. Brakensake. 1982 Hydrologic Modeling of Small Watersheds. American Society of Agricultural Engineers 18 Hadis 2, and 2011. Applicaci Hydrology. Malang, Jogja Media Automa. 19 Hammer, W.I. 1978. Second Soil Conservation Consultant Report. TECH Note Number 10. FAO/Center for Soil Research Bogor. Indonesia. 20 Hewlett, J.D. and W.L. Nutter, 1969. An Outline of Forest Hydrology. Athens, University of Georgia Press. 21 Kennedy, J. and W.E. Watt. 1967 The relationship between lag time and the physical characteristics of drainage basin in southern Ontario. Flood and Their Computations. Proceeding of the Leningrad Symposium Vol. 3. IASH. UNESCO. WMO. Geneva. 22 Lindsley, R.K., M.A. Kohler, and J.L.H. Paulus. 1949 Surface Retention and Detention and Overland Flow. Applied Hydrology. New York. M.C. Grohill Book Co. 23 Lewis Kilovolt, 1975. Quantification of Soil Loss and Sediment Produced from Eroded Land. Soil Science. SOCAMJ Vol. 24. 24 Lindsley, R.K., M.A. Kohler, and J.L.H. Paulus. 1986 Hydrology for Engineers. M.C. Grohill Book Co. New York. IJERT 10 is 060119 www.ijert.org 349. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 25 Moraz, B.1976. A Study of Earthquake Response Spectra for Different Geological Conditions, Bull. Of SISM. SOC. Of America, Vol. 66, No. 3, June. pp 915-935. 26 Moraz, B. 1978, Influences of the Magnitude of the Earthquake and the Duration of Strong Motion on Earthquake Response Spectra, Central American Conference on Earthquake ENG, San Salvador, CA, January 9-12, PROC, pp 27-35. 27 Morgan, RPC 1979. Topics in Applied Geography, Soil Erosion. Longman Group Limited, London. 28 Morgan, RPC 1988. Soil Erosion. Longman Group Ltd. New York. 29 Nash, J.E., and J.V. Sutcliffe, 1970. River Flow Forecasting Through Conceptual Models Part ICA Discussion of Principles, Journal of Hydrology. Vol. 10. 30 Seigel, S. and Merotra, D. 2012. Performance Comparison of Time Series Data Using Predictive Data Mining Techniques, Advances in Information Mining, No. 1, Volume 431 Seed, H.B., Idris, I.M., 1982, Ground Motions and Soil Liquefaction During Earthquakes, EARTH. Engineering Research Institute, Berkeley, California, Monograph, Library of Congress Catalog Card Number 82-84224. 32 Seed, H.B., UGAS, C., Lismer, J., 1974, Site-Dependent Spectra for Earthquake-Resistant Design, University of California, Berkeley, Earthquake Engineering Research Center, Report No. ERC 74-12, November 14, pages 33 Sichuan Water Resources and Hydroelectric Investigation and Design Institute. 2010 Study Report on Dam Filling Material of Jatijid Dam Project. Jakarta, Government of the Republic of Indonesia Ministry of Public Works Directorate General of Water Resources. 34 Snyder, FF 1938. Synthetic Unit Graph. Trans-AM Geophysics Union. Report and Paper in Hydrology. 35 Strahler, AN 1964. Quantitative Geomorphology of Drainage Basins and Channel Networks, in Handbook of Applied Hydrology, Venti Echel, ed. M.C. Grohill. New York. 36 Somarto, C.D. 1986 Hydrology Technique. Usaha Nacional. Surabaya. 37 Soerjono, R. 1978. Kegiatan dan Masalah Dalam Das. Dalam Proceedings Pertemuan Diskusi. Pengelolaan Aliran Sungai. Ditsi. Jakarta. 38 Surapan, 2004. Pelestarian Sumber Daya Tanah dan Air. Penerbit Endi. Yogyakarta. 39 Soewarno. 1995 Hydrology Aplikasi Metode Statistik untuk Analisa Data. Bandung Nova. 40 Sosrodarsono dan Takita, 1980. Hydrology untuk Pengaran. Jakarta, PT Pradna Paramitra. 41 Sriharto, 1993. Analisa Hydrology. Jakarta, PT Grandia Pustaka Utama. 42 Wiesman, W, J.W. Knapp, G. L. Lewis, and T. E. Harbaugh. 1972 Introduction to Hydrology, Harper and Row Publishers, New York. 43 Walpole, R.E., Myers, R.H., Myers, S.L., and Ye, K. 2007. Probability and Statistics for Engineers and Scientists. 8th edition. London, Pearson Education. 44 Ward, R.S. 1974. Principles of Hydrology. 2nd edition. McGraw-Hill Book Company, Limited. London. IJERT 10 is 060119 www.ijert.org 350. This work is licensed under a Creative Commons Attribution 4.0 International License.